Welcome back to the fourth and final section of Chapter 7. This section we're actually going to be returning kind of to where we were at the beginning of the chapter, where we were solving systems of equations. We're just going to be solving systems of inequalities now. This is something that you have done in the past. However, we might have some bigger things, like we'll be including quadratics and stuff in it, in addition to just lines. And then we'll also get into some linear programming. Our learning targets, we're going to graph inequalities of two variables, solve systems of inequalities in two variables, write systems of inequalities from graphs, solve linear programming problems, and solve applications involving linear programming problems. So linear programming isn't like computer programming. It's just systems of inequalities. So the very first thing, graphs of inequalities. When we're graphing inequalities, it's basically the same thing as graphing an equality, like a line or a parabola, except that there are two things that we need to think about in addition to the graph. We need to think about whether or not the line is going to be solid or dotted. Solid lines are going to have an or equal to sign, and dotted lines are just going to be the greater than or less than sign. So we have to know if it's solid or dotted, and then we're going to have to shade one side of the graph or the other. The easiest way of choosing which side is to plug in a point on each side of the line. And I say line, it doesn't have to be like a line. It can be on each side of the quadratic, the inside and the outside. So plug in a point on each, and we're going to shade that. So, an example, this one is in fact a line. We have y is greater than or equal to 2x minus 1. So it's an or equal to, which means that it's going to be a solid line. We're going to graph it. So it's in slope intercept. So we have -1, then we can go up 2 over 1, up 2 over 1, up 2 over 1. Connect the dots. So it's a solid line and it's greater than. So we're going to plug in a couple points. Choose points that are not right next to the line. If my line was not perfectly accurate and I'm choosing something right next to it, it might be on the wrong side. Choose something quite a ways away, for example, and then choose something that's going to be easy to plug in. I'm going to choose this point 0, 5. Why would I choose that point? Well, plugging in 0 is super easy, and it's well away from the line, so I get 5 is greater than or equal to 0 minus 1. Is 5 greater than or equal to -1? Yes, it is. That is a true statement. So we would shade this side of the line. If we plugged something in on the other side of the line, it shouldn't work. So for example, we could go down to -5. If we plugged in -5, -5 is greater than or equal to 0 minus 1. -5 is not greater than -1. That does not work. So this side of the line does not get shaded. And so what this means, anything in the shaded area would be a solution to that inequality. It will give us a y value greater than 2x minus 1. In fact, when it's on the line, it will give us it'll give us a y value that is equal to 2x minus 1. In this case, since it's greater than or equal to, that works. In this next one, if it's on the line, we'd get an equal. Well, equal is not less than, so it wouldn't work. So the solid lines do count, the dotted lines do not count. So let's look at this dotted line. We have y is less than -x plus 3. Same basic idea. We can go up 3. Oh, I'm still green. And then -x, we go down 1 over 1, down 1 over 1, down 1 over 1. We can connect the dots, except making a dotted line. A lot of times what happens is you do what I just about did, and you make the line, and then you think like, oh, is that going to be solid or dotted? I recommend using a pencil, because the cool thing about a pencil is you've got the business end that you made your line with. You've got the other end of the pencil that has this like kind of bouncy thing on it. It's a dotted line maker. So if you think about your dotted line after you make it, it's like, oh, I've got a dotted line maker on the pencil. It comes built in. I mean, how cool is that? We're probably doing stuff on the computer, so you have to choose the dotted line. And now plug in some points. So I would go just straight up or down that y-axis. So it's less than, so hey, the origin. The origin is a great point to plug in as long as we're not too close to it. Over on that first one, we were pretty close. I was just getting away from the line. But we can plug in the origin. Is 0 less than 0 plus 3? Is 0 less than 3? Yes, 0 is less than 3. So we would shade that side. If we plugged in a different point, like say we plugged in 0, 10, 10 is not less than 3. So we would not shade that side. I know that there's always like tricks. It's like, oh, if it's greater than, it's this way. If it's less than, it's this way. That works if it's in slope-intercept form. It does not work if it's in standard form, and it can get you in trouble when we get to like quadratics and stuff sometimes. A safer bet is to plug in a couple points. So we have a couple more graphs of inequalities, and these are going to seem like, oh, well, yeah, that's super easy. Like y is less than or equal to 2. I'm doing this because people struggle with it. Probably because it is too easy and they're trying to overthink it. But we'll actually have a lot of these types of lines. So y is less than or equal to 2. When we have y equals a number, that means the y value is always the same. It is horizontal. So y is going to be horizontal at 2. It's an or equal to. So it'll be a nice solid line. And then we want when it's less than or equal to 2, well, 0 is less than 2, so we can shade down to the 0 part. So we have that side. So now when we have an inequality like this, this cuts the plane into two half planes. It does not matter where the line is. It does not matter if it's diagonal or horizontal or vertical or a quadratic. It cuts into two half planes. You're like, but it's not a half. The plane is infinite. So when you take a piece out, it's still infinite. It's called a half plane. That's just some vocab because it shades continuously going down. So y is less than or equal to 2. It's a horizontal line. How about x is greater than 3? For x equals, we get a vertical line. It's greater than, which means it's a dotted line. And then 10 is greater than 3. So we would shade that side. So those horizontal and vertical lines get people, but that's all they are. Just horizontal and vertical. When you have y equals a number or x equals a number, or less than, greater than, it's just horizontal or vertical. What about quadratics? If we have y is less than or equal to x squared, we're going to graph the x squared, and it's or equal to, so we'll do it in a solid fashion. So we have 0, 0, 1, 1, negative 1, 2, 4, or 3, 9, negative 3, 9, solid, All right, and then we're going to shade either outside of it or inside of it. So let's pick a point. We can pick, if we pick 0, 5, we get 5 is less than or equal to 0 squared. 0 squared is 0. Is 5 less than 0? No, that does not work. We can go -5. So 0, -5 is -5 less than or equal to 0 squared. Yes, it is. And then just to pick other points here, just to show that, so it works here. It's going to work everywhere on this side of that quadratic. So if we picked 5, 0, is 0 less than or equal to 5 squared? Yes, it is. We could pick 10, 10. Is 10 less than or equal to 10 squared? Yes. We could pick -5, 5. Is -5 less than or equal to 5 squared? No, is 5 less than or equal to -5 squared? Yes. And so here, it's this entire piece that gets shaded. We shaded the outside of the parabola. What if we have y is greater than x squared minus 5? So we'd start out 5 down. This is just a vertical translation down 5. And it's dotted this time. All right, we want greater than that, so we can plug in a point. Ooh, we can plug in the origin. Is 0 greater than 0 squared minus 5? Is 0 bigger than -5? Yes, it is. So in this case, we would shade inside the parabola. So a parabola, we shade outside or we would shade inside. Systems of inequalities. Now we had systems of equations. We had a few different methods of solving systems of equations. We had a calculator, which was graphing. We had graphing, and we'd find that point of intersection. We had substitution. We had elimination. And those were the two main ways of doing it. Graphing was more to get an idea of where it would be, but it's really hard, especially if the numbers aren't really nice, to get a good graph for that. For a system of inequalities, the graph is the answer. So if we have this system, we have y is greater than x squared, and 2x plus 3y is less than 4, we can graph these. So let's graph y is greater than x squared. So we just graphed this one. So it's going to be a dotted line. Right? And then greater, so if we plugged in 5, that would be, sorry, 0, 5. 5 is greater than or equal to 0. That works. So we're going to shade. I would shade lightly. I don't really have that option here, unless I wonder. Nope, that's just, I thought, hey, maybe the highlighter will be better. Nope, it's just wider. So we have there, and then we have our line. So we have 2x plus 3y equals 4. When you have lines in standard form like this, I'd graph those intercepts. If y equals 0, 2x is less than 4. Well, 2x equals 4. Divide by 2, x equals 2. So when y equals 0, x equals 2. How about when x equals 0? 3y equals 4. Divide by 3. So y would be 4/3. So dotted line going through those points. And then we need to plug in a value. We can plug in 0, 0. Is 0 plus 0 less than 4? Yes, it is. So we would shade this side. Now the question we're looking for it's where the two graphs intersect. Just like with systems of equations, it's where they intersect. The problem is the graphs are the entire shaded area. So where do the shaded areas intersect? They intersect right in there. Now, everywhere where it's true is a point. Both of these are not or equal to's, so neither of the lines will work. But that area in between will. So sometimes it'll say find a couple points that are solutions. So you would just look in the area. So we have 0, 1/2 would be a solution. We can plug that into both of these. And you can find as many solutions as you need to in that little area. How about this one? This one's a bit bigger. So we have 2x plus y is less than or equal to 10, 2x plus 3y is less than or equal to 14, then x is greater than or equal to 0, y is greater than or equal to 0. There's those horizontal and vertical lines. X is greater than or equal to 0 means it'll be in the first or fourth quadrant. Y is greater than or equal to 0 means it'll be in the first or second quadrant. So this will be in the first quadrant. This is going to happen a lot for us today because we're about to get into linear programming. And generally speaking, in linear programming, it's dealing with positive values. So that just means the values are going to be positive. So in this case, we only need this this graph because these guys are here and here, and we're just going to be in that first quadrant. We don't need to shade, we just need to know we're in that quadrant. So let's look at this first one. 2x plus y is less than or equal to 10. So these are all going to be solid because they all have or equal to's. If y equals 0, 2x equals 10, so x will equal 5. And if x equals 0, y equals 10. And so these two would be connected. And then it needs to be less if we plug in 0, 0. 0 plus 0 less than 10. Yes, so we'd shade this way. All right. How about 2x plus 3y is less than or equal to 14? When y equals 0, 2x equals 14, so x equals 7. When x equals 0, 3y equals 14. So we can divide by 3 to get 4 2/3. Connect those dots. And then it's less than, if we plug in 0, 0, we have 0 plus 0 is less than 14. True statement. So that means that area is shaded. So where's the overlap? The overlap is this whole area. So if we were solving the system of equations, this would be our answer. If we had to choose a couple points in there, 1, 1, 2, 1, 3, 1, 1, 2. There's tons of points in there. All right, and this one brings us to linear programming. We're starting on this slide because linear programming has a feasible region, which is what we just found, and then it'll have what's called an objective function. So in this case, the objective function is just f equals 5x plus 8y. And we need to find the maximum and the minimum in this case. Usually it's one or the other. We're either trying to maximize something or we're trying to minimize something. So it needs to be in the feasible region, which is here. But the wonderful thing about linear programming is there's this very nice theorem that says the maximum minimum values will be at a vertex of the region. So we don't need to plug in the infinite number of points in the middle. We just have 4 points that we might need to plug in. We have 0, 0. We have 5, 0. We have this one over here was 0, and then it was 14 thirds. And then we do need to find this point. So that's going to be the solution to the system of these first two. So we have 2x plus y equals 10. 2x plus 3y equals 14. Notice I just changed them to equal signs because we're interested in the line right now, not so much the area. So what can we do? We can multiply this top one by -1, make that negative 2x minus y equals negative 10. Add these guys together. So we end up with 2y equals 4. So y equals 2. And if y equals 2, we have 2x plus 2 equals 10. So 2x equals 8. So x equals 4. Does that make sense? Well, that was right here. It's pretty close for my graph. So yes, that makes sense. So this is the point 4, 2. Well, I do have an eraser. 4, 2. All right, so now we just need to plug these values into the objective function. So we're going to have points, going to have f equals 5x plus 8y, x comma y, and f. So we have 0, 0, we have 5, 0, 0, 14 thirds, and 4, 2. So we can plug it in. So f equals 0 plus 0. F equals 5 times 5 is 25 plus 0. F equals 0 plus 8 times 14 divided by 3 is 37 and a third. And f equals 5 times 4 is 20, plus 8 times 2 is 16. And so 0 plus 0 is 0, 25, 37 and a third. And 36. So we want to find the maximum and the minimum. For those, you just need to play what game is the biggest number. 37 and a third is the maximum. 0 is the minimum. So that is an example of linear programming that just kind of said, all right, use this objective function. What does that actually look like, though? So we have Negner's produce is purchasing fertilizer with 2 nutrients. N is nitrogen, P for phosphorus. It needs at least 100 units of nitrogen and 90 units of phosphorus. Its supplier sells 2 brands of fertilizer. Brand A costs $10 a bag and has 4 units of nitrogen and 1 unit of phosphorus. Brand B costs $5 a bag and has 1 unit of each nutrient. The produce can pay at most $800 for fertilizer. How many bags of each brand should be purchased to minimize cost? So, the first thing I would look for is the objective function. And for that, you want to see what are we minimizing or maximizing. Maximizing cost. So it's going to be cost equals, we have the 2 types of bags. We have brand A, we have brand B. So the cost for brand A is going to be $10 times the number of bags plus the cost for brand B is going to be $5 times the number of brand B bags. So we have that. Now we need the our feasible region. So we're looking, we have our variables are brand A and brand B. So a couple regions or a couple equations, inequalities that are generally forgotten. We have to have a positive number of bags. All right. And then we need at least 180 units of nitrogen and 90 units of phosphorus. If the supplier sells 2 brands, bag A has 4 units of nitrogen, so we could go 4 times the number of bag A. So this is our nitrogen. And let's see, bag B has 1 of each, so 1B. And we have to have at least 180 units of nitrogen. We'll have a phosphorus. So we need at least 90 units of phosphorus. So it has 1 unit, and brand B also has 1, so A plus B is going to have to be greater than or equal to 90. And then can pay at most $800. So we'll also have that cap, that 10A plus 5B is going to have to be less than or equal to 800, but that probably won't make much of a difference because we're trying to get the smallest cost anyway. So let's graph. Notice in this case 10 to 10 isn't going to work, so have a bigger one. We already have the positive parts, and then we'll have an A-axis and a B-axis. So the first one, 4A plus B, is greater than or equal to 180. So the 180, if A equals 0, B is going to be 180. And if B equals 0, 180 divided by 4 is going to be 45. And we need it to be at least that's going to be greater than that, which means it's going to be on that side. A and B is greater than or equal to 90. Well, that's going to be 90 for both of them. And it's going to be greater. And then $10A plus $5B is going to have to be less than 800. Well, if B equals 0, $10A equals 800, which means A would equal 80. And if A equals 0, we have 5B equals 800 divided by 5, B equals 160. And it has to be less than or equal to 800, so it's going to be less than there. So here our region ends up being this triangle right here, which means our points that we need to plug in are going to be that one, and that one. So we do need to find these points. The first one, we had 4A plus B equals 180, and A plus B equals 90. We could multiply by a negative and add. So we get 3A, B's go away, equals 90, which means A equals 30, B equals 60. That's one of our points. Maybe. So we have 30 and 60. We have these other 2 points, but those 2 points are on the purple line. Every point on the purple line, the cost equals 800. So the other ones are going to be 800. We're trying to minimize. It's probably not going to be the maximum value allowed. So we don't even need to find those points yet. If this turned out to be something bigger than 800, we'd probably want to find those points, but it should not. So we can plug it in. 20 times 30. Nope, 10 times 30. Ooh, that would have come out bigger than 800 probably. 5 times 60. So 10 times 30 is 300. Plus 5 times 60 is another 300. And so that gives us 600, which we're trying to minimize. So that will minimize. So we need 30 bags of A and 60 bags of B. So that is the idea behind linear programming. If, let's say we didn't have that last purple line and our region just went off to infinity, we would be looking at just here. It's not going to be out at the infinite area. It's going to be one of those things. But it doesn't come up very often. It could come up. But again, that's the basics of linear programming. It starts out with solving a system of inequalities and plugging in Our objective function, remember the system of inequalities. The answer is the graph. Make sure that when you're graphing inequalities, you're thinking of the line solid or dotted, and you have to shade one side or the other. So, I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.